Hello everyone. Today we are going to discuss some important oxoanions of D block or transition elements, or say some important oxides of transition or D block elements. So some of the important oxides or oxoanions of transition metals include potassium dichromate, potassium permanganate, potassium manganate, chromic oxide. So these are some important oxides which are often used in inorganic as well as organic reactions. So we are going to discuss these important oxoanions or oxides of transition elements, their preparation, their structures and their properties. So to begin with, let's start with potassium dichromate. Potassium dichromate K2Cr2O7. So first of all, let's start with preparation of potassium dichromate. This potassium dichromate is prepared or manufactured from chromite ore. So let's discuss the steps involved in preparation of potassium dichromate. So the first step is we have a chromite ore FeCr2O4 iron chromite. Now this iron chromite FeCr2O4 is fused with sodium carbonate in presence of an oxidizing agent like aryl oxidant. When this gives you sodium chromate, which is yellow colored solution. So we have this iron chromite solid fused with sodium carbonate solid in presence of an oxidizing agent from air. When this gives you sodium chromate, this is aqueous solution and this is yellow color plus Fe2O3 plus carbon dioxide So fusion of this iron chromite with sodium carbonate in presence of aryl oxidant, which is an oxidizing agent, gives you a yellow colored sodium chromate solution. This is sodium chromate. Now, the reaction involves fusion of this compound with sodium carbonate in presence of aryl oxidation. So, solution is basic in nature because this sodium carbonate reacts with water to give you sodium hydroxide. So, reaction is highly basic in nature. So, in the second step, what we have to do is the solution, yellow color solution, which is basic in nature, is acidified with sodium, so it's with sulfuric acid. So in the second step, we have this Na2CrO4 sodium chromate. This aqueous solution, yellow. This is acidified with acid. We can take sulfuric acid. So on acidification of this yellow color sodium chromate, this changes to sodium dichromate, which is orange color. So acidification of yellow color solution containing sodium chromate with a sulfuric acid gives you sodium chromate. So this will give you sodium sulfate aqueous solution. So yellow color sodium chromate is converted into orange color sodium dichromate. Now this sodium dichromate is highly soluble in water. So this sodium dichromate, which is highly soluble in water, is converted into less soluble dichromate on reaction with potassium chloride. So we have sodium dichromate reacts with potassium chloride aqueous solution. When this more soluble sodium dichromate is converted into less soluble potassium dichromate crystals. So crystals of potassium dichromate comes out. So this is the process involved in preparation of potassium dichromate from iron chromate. So I repeat again. So the iron chromate is first fused with sodium carbonate in presence of aerial oxidation as acting as an oxidizing agent. When this is converted into yellow color sodium chromate solution, being basic in nature, is acidified with sulfuric acid. When yellow color chromate is converted into orange color dichromate. Now sodium dichromate, being more soluble in water, is converted into less soluble potassium dichromate on reaction with HCl. So we have this precipitate of potassium dichromate crystallized out. This is the structure. Now if you look at this second step and third step, we have chromate. Now chromate is converted into dichromate. So while if you look at it, this is the method of preparation. Then coming to the structure. Structure of this oxoanion will have this CrO4 2 minor. This is chromate ion. In the second step of this reaction, we convert this chromate ion into dichromate, that is Cr2O7 from CrO4. So I'll discuss how this exists in two different pH. So first coming to this chromate ion. Now in this chromate ion, this chromium, this is undergoing sp3 hybridization. If these undergoes sp3 hybridization, the shape and the geometry of this oxoanion will be tetrahedral. So we have sp3 central atom chromium is undergoing sp3 hybridization. Shape and geometry is tetrahedral. So if this is the hybridization, then if you look at the structure, we have this chromium. This is oxygen, this is oxygen, this is oxygen. We have 4 oxygen attached to this chromium. We have 2 negative ends, so we have 2 oxygen carrying 2 negative charges, and the remaining 2 oxygen forms double bond with oxygen. So if you look at this, if you join this corners, we get a regular tetrahedron. So chromium is at the center of tetrahedron, and for these four oxygen occupying the four corners of regular tetrahedron. Now if you look at this, we have two oxygen which is attached to chromium through single bond, and the remaining two oxygen is bonded to chromium through pi bond. Now the question is, these oxoanion, that is chromate CrO4 2 minus n, how this pi bond formation takes place. These two pi bonds, this is pi bond. Now this pi bond is formed by p pi d pi bonding. P pi of oxygen transferring electrons to d pi of chromium. So because of this transfer of electron density from filled p orbital of oxygen to vacant d orbital of chromium, this oxoanion is stabilized by this p pi d pi back donation bond. So because of this thing, this oxoanion is being stabilized. Now if you look at this, these negative charge will be delocalized over this 4 oxygen atom. So at the exact bond order between these chromium and the oxygen is between single bond and double bond. So this is slightly greater than single bond but less than double bond. And if you look at this bond length, again the bond length is between single bond and the double bond. So this is we have chromate ion. If you in this chromate ion, the chromium, the central atom chromium is in +6 oxidation state, that is the highest oxidation state of the chromium. Now coming to the structure of dichromic anion, Cr2O7 2 minus. In this dichromate, again chromium is +6 oxidation state. So both chromate ion and dichromate both are having +6 oxidation state. Dichromate ion. Now in this dichromate ion again, the chromium, the central atom chromium is undergoing sp3. So the shape and geometry this is perfectly tetrahedral. The only difference is in this case we have one chromium, in this case we have two chromium, so we have two tetrahedral units shared or joined through a common oxygen. It is two tetrahedral units joined through a common oxygen atom. So we have looked at this chromium, so we have two chromium, means we have two tetrahedral units. These are two tetrahedral units, and these two tetrahedral units are joining through a common oxygen atom. So there is a common oxygen between these two tetrahedral units. We have two chromium, 7 oxygen, and 2 negative charges. So we have negative charge on this oxygen, negative charge on this oxygen, and the rest is double bond. This common oxygen is bonded through both these chromium through single bond. Now, similar looking at this structure, again this pi bond, that is again formed by p pi d pi. Electron is transferred from filled p orbital of oxygen to vacant d orbital of d, resulting in stronger bond, and which results in more stabilization of this dichromate ion or chromate ion. So both chromate and dichromate is stabilized by p pi d pi bond. Filled orbital of oxygen, filled p orbital of oxygen to vacant d orbital of chromium. So this is the structure of chromate and dichromate, both having +6 oxidation state, highest oxidation state that is possible for chromium ion. Both the central atom is chromium, having sp3 hybridization. Both are tetrahedral shape as well as geometry is tetrahedral. Both contains p pi d pi bond, in which electron is transferred from filled p orbital of oxygen to the vacant d orbital of chromium. So this is the structure of chromate and dichromate. So both are interchangeable, means both we can convert this chromate into dichromate or dichromate into chromate, and that is what we call as pH dependent structure of chromate and dichromate. Now coming to that, so we are coming to the properties. First, effect of pH. So we have this chromate CrO4 2 minus, and we have Cr2O7 2 minus. In both these, chromium exists in +6 oxidation state. These chromate can be converted into dichromate, and dichromate can also be converted into chromate ion depending on pH. Now, while preparing this dichromate from chromate, we make the solution to be acidic. That means on acidification or in acidic medium, this chromate ion changes to dichromate. That means dichromate ion is stable in highly acidic medium, whereas this chromate ion is stable in highly basic medium. So on acidification, that is pH less than 7, this chromate ion changes to dichromate. Or starting with this dichromate, if the solution is made alkaline, so ultimately this dichromate changes into chromate. So that means this dichromate, this is stable in strongly acidic medium, whereas this chromate ion, this is stable in basic medium. This chromate ion, that is yellow color, dichromate ion is orange color. So in acidic medium, yellow color chromate ion changes to dichromate, and in basic medium, this orange color dichromate changes to chromate ion, which is yellow color. In both the cases, chromium is central atom, chromium is sp3 hybridized, chromium is tetrahedral. The only difference is the oxoanion. So dichromate is stable in acidic medium, chromate ion is stable in basic medium. So if we manage the pH, then this one can be converted into the other. That is pH dependent effect. Second property. Now this dichromate reacts with peroxo compound. with peroxides. So we have this dichromate Cr2O7 2 minus reacts with hydrogen peroxide in presence of acid. So when this dichromate reacts with hydrogen peroxide in presence of acid, this gives you deep blue color compound CrO5, which is also written as CrO. In this again the chromium is +6 state. This is deep blue colors. So this is chromium peroxide. Now if you look at this chromium peroxide, this chromium, we have 4 oxygen is peroxide ion and 1 oxygen is normal oxide. So if you look at this structure, we have this. So this is what we call as butterfly structure. Now these 2 oxygen, this is peroxide. This is peroxide, this is normal oxide. So we have 2 different types of oxygen. This normal oxide, this carries -2 charge, peroxide carries -1, -1. So oxidation state of chromium is +6. So this is when dichromate reacts with hydrogen peroxide in acidic medium. In much stronger acidic medium, Cr2O7 2 minus plus strongly acidic. When this gives you tetraperoxo ion or CrO8 3 minus. Tetraperoxo species. This is brown color. So we have 4 peroxide ions attached to chromium, and the chromium in this case is +5 oxidation state. Now coming to the structure of this, we have this chromium. This is the structure of tetraperoxo species, and each oxygen is having peroxide and there is no normal oxide. This is peroxide ion. Each peroxide ion carries -1. Charges on each oxygen is -1. So there are 8 minus. We have 3 minus, so this comes out to be +5 oxidation state. So in acidic medium, this dichromate is converted to peroxide compounds M is chromic manganese in +6 or chromic manganese in +5. This is with peroxides. Now we have this dichromate A2Cr2O7. In this dichromate, potassium dichromate A2Cr2O7, if this is heated with sulfuric acid, when this is converted into CrO3, chromium trioxide, chromium +6 oxidation. Now this chromium trioxide, this is commonly known as chromic acid, which is a very good oxidizing agent used in organic chemistry. And one of the most important property of potassium dichromate is an oxidizing agent. As an oxidizing agent. So as an oxidizing agent, if you look at this, we have Cr2O7 2 minus chromium +6 oxidation state. Whenever this chromium reacts, this always reacts in acidic medium. When this changes to chromium +3, so if you look at this, each chromium changing from +6 to +3, since there are two chromiums, so total change in oxidation state is 6 moles of electrons is involved in this. This is the half region in which chromium the dichromate and acts as oxidizing agent. So the N factor of this dichromate and in this reaction is always 6. So as an oxidizing agent, this dichromate is a very strong oxidizing agent. So this acts as an oxidizing agent in presence of acidic medium. So let me give you some important reactions in which dichromate acts as an oxidizing agent. Both organic and inorganic species can be oxidized by this dichromate. Now this I minus iodide can be oxidized by Cr2O7 minus in acidic medium to iodine -1 to 0, and this chromium changing from +6 to +3. So the reaction is not balanced. I'm just showing this chemical structure. So I minus is oxidized to molecular iodine. Now we can have sulfide ion H2S, sulfide H2 minus. This H2 minus can also be oxidized by dichromate ion to give you sulfur -2 to 0, and chromium is converted into +3 oxidation state. All this reaction is still happening in presence of acid. So we have I minus to I2, hydrogen sulfide to means sulfide ions to 0. We can have this ferrous ion. Now ferrous ion is oxidized to ferric ion in presence of dichromate ion in acidic medium. So these are some of the inorganic species which can be easily oxidized by dichromate. Now many of these organic compounds can also be oxidized by this dichromate. Now coming to organic reactions, we have this aldehydes. This is aldehydes. So aldehydes can also be oxidized by dichromate in acidic medium to give you carboxylic acids. So aldehydes are oxidized to acids. We can also have primary alcohols. Now these primary alcohols will also be oxidized by dichromate ion in presence of acid. When this is first oxidized to aldehyde, and aldehyde is further oxidized to acids. In the same way, look at this, we have this or aniline. These type of organic compounds is oxidized by dichromate in acidic medium to give you benzophenone. Sorry, quinone. So either we have phenol or aniline or para compound. These compounds on oxidation with dichromate, this is converted into quinone. So if you look at this, in all this reaction, chromium is changing from +6 to +3. So chromium in +6 oxidation is, that is orange. Now when this chromium +6 changes to +3, the chromium in +3 oxidation, this is green color. So if there is change in color of the solution from orange to green, that means some reaction has taken place, and the possibility is this dichromate and this chromium is +6 now getting reduced to chromium +3, so that this gives you green color solution, and the other compound has been oxidized. So this is potassium dichromate as an oxidizing agent. Now, in inorganic titrations, volumetric analysis, potassium dichromate is used as a standard reagent. Now, in all these reactions, we never use sodium dichromate. The reason being, sodium dichromate, though is more soluble than potassium dichromate, sodium compound, that is sodium dichromate, is hygroscopic in nature. That means it keeps on absorbing water molecules from atmosphere. So this being hygroscopic, its nature keeps on changing, whereas the potassium compound is not hygroscopic. Hence, this potassium dichromate is more preferred in inorganic titration and is used as a standard reagent for volumetric analysis or titrations. So, if suppose questions is why is potassium dichromate is preferred over sodium dichromate for volumetric analysis, so the reason is sodium compound is hygroscopic whereas potassium compound is not hygroscopic. So, if you are using sodium chromate, so before starting we have to standardize the solution. But in case of potassium dichromate, there is no need for standardization because potassium dichromate is not hygroscopic in nature. So these are preparation as well as the properties of potassium dichromate. Having done this potassium dichromate, one more important compound that is left is potassium permanganate. Now let's go to potassium permanganate. Potassium permanganate. AmNO4. Potassium permanganate. Now coming to the preparation point of view, let's discuss the steps of preparation. Now this potassium permanganate KMnO4 is prepared from pyrolusite ore, which is not contains MnO2, pyrolusite ore, that is an ore of MnO2. Now this MnO2, manganese dioxide, is fused with alkali. fuse with alkali in presence of an oxidizing agent like potassium nitrate or aerial oxidation. Potassium hydroxide plus oxygen from air or KNO3. So fusion of this pyrolusite ore containing manganese dioxide with alkali, that is potassium hydroxide, in presence of an oxidizing agent, when this gives you K2MnO4. This K2MnO4, again this is solid, Mn in plus 6 oxidation state. This gives you dark green color KMnO4. Now this dark green color KMnO4, that is K2MnO4, this undergoes disproportionation in acidic medium or neutral medium. Acidic or neutral undergoes disproportionation to give you KMnO4, Mn in plus 7 oxidation state plus MnO2. This is purple or pink color. So in the first stage, this pyrolusite ore containing MnO2 is fused with potassium hydroxide in presence of an oxidizing agent, when this gives you dark green color potassium manganate. This is potassium manganate. In the second step, this potassium manganese undergoes disproportionation in presence of acidic or neutral medium to give you purple color or this potassium permanganate. Commercially, in the commercial method, the dark green color potassium manganate obtained in the first step, means the first step remains as it is. So after this fusion of this MnO2 with alkali in presence of air or oxidizing agent, when it is converted into dark green color potassium manganate, this dark green color potassium manganate is electrolytically oxidized in presence of alkali to give you this MnO4. So we have this MnO4 2 minus, that is dark green, Mn plus in presence of alkali, electrolytic oxidation, when this gives you MnO4 minus, Mn plus 7. So commercially, dark green color potassium manganate obtained by fusion of this MnO2 with alkali in presence of oxidizing agent is electrolytically oxidized in alkaline medium to give you MnO4. Now, in laboratory, that is in laboratory lab, this manganese ion Mn plus 2 is oxidized by peroxodisulfuric acid. This is oxidized by peroxodisulfuric acid, when this gives you MnO4 minus plus sulfur. So either we can go for this commercial method. This is the commercial method, electrolytic oxidation. That is laboratory method for small scale preparation. This is general method of preparation. So this is how we prepare potassium permanganate. Now coming to the structure of this potassium permanganate, we have this MnO4 minus Mn is plus 7. The central atom Mn is again undergoing sp3 hybridization. So shape and geometry, that is tetrahedral. So let's write down the structure of this. We have the central atom Mn. We have 4 oxygen. We have 1 negative charge. So we have oxygen with negative charge. Rest of the oxygen is forming multiple bond with Mn. Now, similar to dichromate ion, these multiple bond that is being formed here, this multiple bond, that is this bond, this pi bond, this is pi bond, and this pi bond is formed by p pi of oxygen transferring electrons to d orbital of Mn. So both dichromate, chromate, or this permanganate ion or manganate ion, all these are stabilized by d by Beck donation. We have this MnO4 2 minus manganate ion plus 6. Again, this is sp3. So we have this is again p by d. If you look at this, Mn plus 6 contains 1 unpaired electron, so this is paramagnetic due to the presence of 1 unpaired electron. Mn plus 7 doesn't have any unpaired electron, so this is diamagnetic. Now, both potassium dichromate and potassium permanganate, the central atom chromium or manganese is the highest oxidation state. So these doesn't have any d orbital, so there is no chances for color of these ions. But if you look at this, dichromate ion or the chromate ion or this potassium permanganate, all these are intensely colored. The color of these oxoanions having 0 electron in d orbital is due to a mechanism known as charge transfer complex, in which an electron is momentarily transferred from oxygen to the central atom, reducing the oxidation state of the central atoms to +6 in case of Mn, +5 in case of chromium. So this single electron undergoes excitation, de-excitation, resulting in the release of energy which falls in visible spectrum, giving rise to intense structure. So simply saying, the charge of oxoanions containing d0 electron is due to a mechanism known as charge transfer mechanism. So these are the structures. Now coming to the properties. MnO4 is a very strong oxidizing agent. This reacts in 3 different ways. MnO4 minus in acidic medium, this changes to Mn plus 2. So Mn plus 7 is changing from plus 2, so the n factor is 5. There is total change in oxidation state by 5 units. So in acidic medium, this is the reason MnO4 always changes to plus 2. Now, in alkaline medium, MnO4 changes to MnO2. So there is a change of 3 electrons. So the N factor is 3 here. In neutral medium, this changes to so N factor is 1. So depending on the medium, this MnO4 reacts to give you different products. In all these cases, the total change in oxidation is different, so N factor is different. So whether we have this or this different thing, but the main important property of potassium permanganate is as an oxidizing agent. It's a very strong oxidizing agent. So as a look at this I minus can be oxidized to I2 in acidic medium. We have ferrous ion is oxidized to ferric ion again in acidic medium. We have this sulfide ion is oxidized to sulfate by this KMnO4. We can have this nitrite is oxidized to nitrate in acidic medium. We can have this sulfide ion is oxidized to sulfur. We can have this C2O4 oxalate ion in which carbon is in plus 3 oxidation state is oxidized by KMnO4 to carbon dioxide in plus 4. So carbon is oxidized from plus 3 to plus 4. In this chemical case, we have I minus is oxidized by KMnO4 in alkaline medium to give you iodate ion. So I minus is changing from plus 5. So this is how KMnO4 acts as an oxidizing agent. It means we have a number of inorganic species which can be oxidized. Apart from this, we also have organic compounds. So primary alcohol oxidized to acid. If we have this secondary alcohol, this is primary. Secondary is oxidized to ketone. We can have a look at this aldehydes. So aldehydes are oxidized to acids. Same way we can have phenol, aniline, para-dihydroxybenzene, para-diaminobenzene. All these species is oxidized by KMnO4 to give you quinone. Apart from this, side chain substituted benzenes benzene with side chain substitution like ethyl, this is oxidized to direct benzoic acid. But if you have this tertiary butyl group, this is not oxidized. So any side chain, if this is attached to benzene, this is also oxidized. So this is as an oxidizing agent. So this oxoanions, dichromate, chromate, potassium permanganate. These are very strong oxidizing agent which finds its application in organic as well as inorganic reactions. Now, if KMnO4, potassium permanganate, is used as an oxidizing agent in volumetric analysis, that is titration, no indicator is required because these KMnO4, MnO4 minus, acts as a self-indicator. During the course of reaction, the color changes from pink to other color. So if KMnO4 is acting as an oxidizing agent, so this will always oxidize the other species and itself will be reduced. So on reduction, Mn oxidation state changes from +7. So +7 is intensely pink color, so pink color will discharge. If there is a discharge, the point at which the pink color is discharged will be considered as the end point of titration. So KMnO4 titration, there is no indicator required. MnO4 minus itself acts as a self-indicator. So this is all about some important oxoanions of transition elements. So we have discussed properties, preparation, structure, geometry, and their properties. So we'll conclude with this. Thank you all.